Okay, so we're going to talk about confidence intervals, bootstrapping, types 1 and 2 errors, and power. So we're going to start with samples. Remember, a sample is a selection of objects or observations taken from the population of interest. For example, say we'd like to know the mean body mass index in adolescents aged 13 to 19. We can't measure everyone, so we take a sample of 100 and we get an average. Because our sample is only a selection of individuals from the population, it will never be perfect representation of the population. Different samples of the same population will give different results, and this is called sampling error, or variation due to sampling. Some sampling error will always be present. When we express an estimate of a population parameter, we should include a confidence interval with our point estimate, as communicating how accurate our point estimate is likely to be. So far, we've only been doing point estimates. So suppose our research question is, what is the mean body mass index for adolescents aged 13 to 19 years? We take our sample mean, which is the best estimate of the population mean, and we use a confidence interval to express the range in which we are pretty sure, 95% of the time, that the actual population parameter lies. The width of the confidence interval depends on two things: the variation within the population of interest and the sample size. Variation. If all the values in the population were almost the same size, then the sample would have little variation and our estimate would be pretty close to the population value, and our confidence interval will be small. Conversely, if the sample is more varied, the confidence interval will be wider. So the sample size. The smaller the sample, the larger the sampling error, because we will have less information from which to draw inference about the population. The effective sampling error is reduced with larger sample sizes. So, when we're doing normal base calculations, when we use the traditional confidence interval formulas, which are found in the book, the stated level of confidence influences the width of the confidence interval. So if we're 90% confident, our alpha is equal to 0.1. If we're 95% confident, we set our alpha equal to 0.05. If we're 99% confident, our alpha was set at 0.01. All estimates of population parameters should be expressed as confidence intervals. We're going to let the computer do this. Alright, so bootstrapping. This is something that was not even available in SPSS about 3 or 4 years ago, but it's now a simple button to click. I'm going to show you what it is because the book talks about it, and then we'll just use regular confidence intervals going forward. But simply put, in a simple random sample of size n, a bootstrap sample is another random sample of n values obtained with replacement. Why would we want to do this? A bootstrap sample is a smaller sample that is bootstrapped, which comes from that saying, pull yourself up by the bootstraps, from a larger sample. Bootstrapping is a type of resampling where large numbers of smaller samples of the same size are repeatedly drawn with replacement from a single original sample. Bootstrapping is loosely based on the law of large numbers, which states that if you sample over and over again, your data should approximate the true population data. This works, perhaps surprisingly, even when you're using a single sample to generate the data. So, let's consider a new question. Suppose we did a study that measured the number of errors made in a given laboratory. Our research question is, were there any errors in laboratory A? Our hypotheses are, the null hypothesis is that the mean of the errors, I should have a subscript error, the mean is 0, and the alternate hypothesis is that the mean is not equal to 0. So it's a two-tailed test, because we're not designating any direction. So we go to Analyze, Compare Means, One Sample T-Test. I can click on this bootstrap. I click Perform Bootstrapping. It auto-populates 1,000 times. I usually click the Bias Corrected Accelerated and just let it go. Click Continue. And then we get the output here. We have the regular one sample t-test and then the bootstrap for one sample t-test. And you can see that we had a significant test. Here our significance is slightly larger. Our p-value rather is slightly larger. And then here are these are the regular confidence intervals using the calculations that we would use if we did it in the book. 3.9 and 5.8, and here we have 4.1 and 5.7. Very close, but they're a little bit, this is a little bit tighter, right? These numbers are closer to each other than these numbers are. If your confidence, another thing to note, if your confidence interval upper and lower limits span or encompass 0, then your test is not significant. This is another way to use the confidence interval way of determining whether or not you have a significant test. If 0 were between here, so if this was a negative number and this was a positive number, then 0 is here, it would be not significant. But because it's significant, both of these guys are on the positive side, or they could have both been on the negative side. Here, our confidence interval upper and lower limits do not span 0, so our test is significant. All right, writing up the results. In APA, which is the American Psychological Association, which is what I use for my own research, results, you would write it up like this. Results for the given sample are T of 29 is equal to 10.6, P is equal to 0.01, 95% confidence interval, 3.92 and 5.81, Cohen's D is equal to 1.9. What does all that gobbledygook mean? Okay, so here's my T value. All right, T is equal to 10.6. So I round it up. Where did this 29 come from? That's my degrees of freedom. Okay, here's my P value. It was given at 0.00, but I told you guys never to use 0.000. Always just put a 1 in there. 0.01. 95% CI stands for confidence interval, and then I gave these ones, 3.9, 2, and 5.81. I could have just gone to one decimal place. And then I said Cohen's D with an apostrophe S, and I calculated that out by doing the mean difference divided by the standard deviation right over here. The American Medical Association is very, very similar, but you'll notice that they don't use parentheses, they use a subscript for the degrees of freedom. They don't like spaces around their equal signs, and everything else is the same. And then here, the 95% confidence interval goes inside the parentheses, and then they report them. And then their Cohen doesn't have an apostrophe S, and again, no spaces. I do not care one way or the other which way you do it. I just want it to be consistent. So going forward, I'm going to be using APA because I don't even have to look those up. AMA, I do have to look those up, so I'll just do APA. If you guys want to do AMA, I have the website in this PowerPoint that you can use. It's very simple. So we would write it up. Our hypothesis that the mean laboratory errors was 0 was rejected. Cohen's D shows a large effect size, meaning there is a strong evidence of errors in this laboratory. This is made up data. In order to evaluate lab errors, you would have to operationalize how you were quantifying that. Instrument malfunction, or human error, or both, and measure it in some way. That's just a little sidebar. So in short, when reporting the results for your statistical tests, we will include confidence intervals. So I want the confidence intervals in your homework assignment, or your SPSS homework assignment. And SPSS gives us those, and I don't need bootstrapping. If the confidence interval spans 0, like this one, then the test was not significant. If it doesn't span 0, like this one, then it is significant, but you always can just look at the p-value. And then again, here's the style guide. I use APA because that's what I'm familiar with the best. If you want to go further information about AMA, here's an excellent website. Choose whichever style guide you want in your final project. All right, type 1 and type 2 errors and power. So this is a very easy way to remember what type 1 error is. False positive. Here we have a man, and the doctor's saying, you're pregnant. Obviously, false positive. Man can't be pregnant. All right, here we have a type 2 error, false negative. Woman visibly pregnant, and the doctor's saying, you're not pregnant. So type 1 error is the false positive. Type 2 error is a false negative. A type 1 error, right here, and I showed you guys this when we did sensitivity and specificity because it's very, very much related to that. A false positive is the probability of rejecting a true null. So the null hypothesis is true, but we rejected it. So that's the, we rejected a null that was true. We use alpha to represent this. Alpha is equal to the probability of making a type 1 error, and it's equal to the probability of making a false positive. A type 2 error is the mistake of failing to reject a false null. Here it is beta. We use beta to represent this. So beta is equal to the probability of making a type 2 error, which is equal to the probability of a false negative. All right, so we have alpha, we have beta, and then we have this thing called power, which is 1 minus beta. Okay, and then we have true negatives. So we can choose alpha. So how do you minimize the chances of an error? You set the probability of making a type 1 error you are willing to tolerate in an experiment in advance, and it's called the alpha level. We've already experienced this. We know what this is. This is decided a priori, which is Latin for before the experiment. So alpha, like I said, is the probability of making a type 1 error. The convention typically is to set the alpha level to be no more than 0.05 or 5%, but what does that mean? It means that the chances are less than 5% that you have an oddball sample, false positive result. You could still have an oddball sample. Your chances would be 5%. It would happen one time out of 20. What you're saying is that you will not regard any result as statistically significant unless it is one that would occur less than one time out of 20 simply by chance. In other words, you would accept it only if it's at least 95% certain that it wasn't just a fluke. All right, and then beta. So remember that beta is the mistake of failing to reject a false null, and that's called beta. So probability of making a type 2 error is probability of making a false negative. In order to minimize this, we calculate the power of an experiment needed to minimize beta. The reason why we use the word power, so power is 1 minus beta. The reason why we use the word power is that it measures the power to distinguish an effect when it is there. It measures how powerful the experiment is. It gets at how small an effect the experimental microscope will distinguish. So you want beta error typically to be less than 20%. So you want power to be 1 minus beta of about 80%. Then you have an 80% chance of finding an effect if it's there. So if the beta error is 20%, then the power is 80%. So if the effect is there, you have an 80% chance of detecting it. The reason why you don't go for more is that you reach a point of diminishing returns at 80%. You have to get bigger and bigger samples, and it costs too much money. So typically you set the alpha 0.05 and power at 0.8 or a beta of 2. Just remember a power of 80%. Okay, so calculating power. Power can be established for experiments by calculating how large a sample size needs to be in order to achieve the power set at 80%. And all of this is just a whole lot of information, but I just want you to know what these concepts are, because if you're ever in a situation where you're going to be doing a research study and they want you to establish 80% power, I want you to know what this is. It means that you're going to find an effect if there's an effect to be found. And the way you do that is, like alpha you can set a priori. You could just say, you know what, we're going to use alpha at 0.05. But you can't do that with beta. You don't know what you're going to get. So you manipulate the sample size so that you set your power at 80%, and that's kind of the best you can do. All right, so that's all I'm going to say for power right now. We're going to do power analysis that you'll need to use for your thesis. I'll do that later on in the semester toward the end.